So in the last problem we talked about in the last video, our definite integral had a negative value. So that meant that for that problem, the definite integral does not represent the area of the region formed by the graph. However, if a function is continuous and non-negative on a given interval, then the definite integral does define the area of the region. So if f is continuous and non-negative on the closed interval from a to b, the area of the region bounded by the graph of f, the x-axis, and the vertical lines x equals a and x equals b is the definite integral from a to b of f of x with respect to x. So for now, to evaluate a definite integral, we can either use the limit definition or we can recognize the area of geometric figures in some cases. We're going to get another method in section 4.4, but for now these are the two that you have. So I am well aware that many of you have graphing calculators that can evaluate definite integrals, but you're welcome to use these to check your answers, but if you just say definite integral equals and then you give me a long decimal number without showing any work, you are not going to get full credit for this problem. You will may get 1 point at best. So do not become dependent on your graphing calculators. You have to actually be able to evaluate the integrals. Okay. So let's take a look at what this means when I say you can evaluate a definite integral by recognizing the area of a geometric figure. When in doubt, always graph your function that you're trying to integrate because this could help you determine an easier way to do it. So in this case, we're taking the integral from 2 to 5 of 2 with respect to x. So f of x is equal to 2. And if I graph that, that just looks like a horizontal line at y equals 2. And I'm going from 2 to 5. So I've got vertical lines here and here. And you can see that the shape that's formed here is actually a rectangle. Now this whole shape is positive. So this is actually the equal to the area of a rectangle where the width is 3 units here and the height or the length is 2 units here. So this is just going to be equal to 3 times 2, or 6. That's the value of that integral. A lot easier than the limit definition if you can do it. In this case, we've got f of x equals negative x plus 2. So if I go to graph that, I'm going to go down 1 over 1, down 1 over 1, and this is not to scale, but you get the idea. This is going to be a triangle. So my shape is going to be a triangle. And we're going from 0 to 2, so that is the shape we're looking for. So this is going to be the area of a triangle where the base is equal to 2 and the height is equal to 2. And it is all positive, so we're good there. So we know that this is base times height over 2, or 2 times 2 over 2, which is 2. Now this one is one that works out fantastically with a geometric representation because this would be kind of a beast if you were trying to integrate this using the limit definition. So keep in mind that f of x is going to be the square root of 9 minus x squared. So this is the same thing as saying y is the square root of 9 minus x squared. So if you square both sides, you get that x squared plus y squared equals 9. So this is going to be a semicircle where the center is 0, 0, and the radius is 3. So since we've only got the positive square root, we only want to look at the positive half. So it looks like this. And you can see that it is all positive in this region. So this is the area of a semicircle of radius 3. So this is going to be 1/2 times pi r squared because the circle would be pi r squared. So that's 1/2 times pi times 3 squared, or 9/2 pi. And that would be the value of my definite integral. Now again, this is very important. If any of the shaded region falls below the x-axis, you cannot use this method. You can consider the area below the x-axis negative if you want to, but you can't just straight up say it's the area of the shape.